Tom Mathews from Mathews Engineering here. I wanted to show everybody a very interesting view of space-time and general relativity that shows how the curvature of moving objects truly is the curvature of space and nothing else. And it's going to seem weird at first, but I think this demo, I'd never seen anything like this before, and I realized I could do a pretty good mock-up of this in this 3D design software that I like to use. This is Viacad. It's an excellent 3D package. But anyhow, what I've got here is imagine a baseball thrown up in the air. It traces out a parabola just like we were taught in high school physics, and we're used to seeing that shape. The other thing that we might imagine is what if a light beam went by at the same time, and this blue line is a light beam, and it's very straight the way we would expect it to be. So these ideas of curvature here are interesting, but it's hard to reconcile these with what you might be used to seeing. This is the typical example that most Discovery Channel shows show. They show a fabric table or a pool table with pool balls warping the table. But this is confusing to me because this implies that all the warping is in space, and it doesn't really drive home the 4D space-time concept. And the warping is truly in time and space, not just space. This image is off the European Space Agency website. But let's go back to our demo here, and here's the parabola of the baseball. Here's the light beam. Let me turn on some coordinates for us so we can see what we're looking at. So here's space, which is where we're used to living, and the light beam is very straight. In this example, I've made the light beam is 100 times faster than the speed of the baseball, which, of course, in real life it's much, much faster than that. But this will help us exaggerate this effect so you can see that the curvatures of this blue line and the green line are indeed the same, which, seems like just impossible from this view. But I'll show you why they're the same, and it's very interesting. So again, if we could imagine that if we could step out of space, instead of just living in space, if we could step back and look at the world from the perspective of space-time, and what I'm going to do with this software is I'm going to rotate these curves, and then let's turn on the time axis. So let's rotate a little more. So time is going that way, and notice that that curve is not quite so aggressive when you see it in time. And both of these lines are exactly 1 unit long. So in four-dimensional space-time, everything travels at the same speed all the time. There's only one speed, and that's the speed of light. And so, how do you reconcile that? So an object that we think of as moving slowly, like this baseball, is actually all of its speed is directed through time and not through space. But it travels the same distance in 4 space as the light beam does. Only when we look at it from above, like let's look at it from above, and you can see that these two lines are really the same length. So imagine this is a 10-second interval, but 10 seconds in time would be the amount of distance that we would travel in that amount of time at the speed of light. But only when we look at them from the front, let's look from the front again, do we see what we see in our world, which is this parabola. But when we zoom back, we can see that they have the exact same radius of curvature. Now the question is, what is causing the radius of curvature? And what it is let's zoom back some more here. So here's an object down here, and that would be the Earth, or a black hole, or some other gravity producing source, the sun. But let's look again at the radius of curvature. I've got some construction lines I've made here, and here's the construction lines for the light beam. So these are radiuses of a circle. So this is a arc circle, and here's one for the ball, and we can see that they both go down to the same length. So they both have the same radius of curvature. And let's see where they go. Now, why do they don't go to the same exact point? They really are going to the same point because remember, the ball is moving through time with the Earth here, and the center of gravity of the Earth moves along with this cylinder as it moves through time. So that center moves along with the ball. But again, when we zoom in, look, they're both exactly the same radius. It's only when we see the world from our bizarre perspective, which is looking end on here. If we go right in here, end on, we can see that this starts to look like a parabola and the light beam looks like a line. Let's look at it again exactly from the front, and we see the parabola and the line. So every day when you see an object, a ball thrown up in the air at the baseball game, you are indeed seeing the curvature of space-time. And it's something that's real. This is, of course, Einstein's general theory of relativity. It's fascinating, and it's only when I started thinking about it in this terms that I understood, because those pool ball, tables are interesting, but they don't really get to the point that all of these world line curves for an object moving, freely through space have the exact same radius of curvature when viewed in 4 space. I hope this is helpful. I'm Tom Mathews from Mathews Engineering, and thanks for listening.